think everyone here knows Arwen. She's the Executive Officer of BBIFMAC, and obviously a very well-regarded water quality scientist. And we're very fortunate that BBIFMAC are part of the BIP project, because it actually allows us to sort of trace the practice change on farm with the irrigation automation, or the irrigation practice change, and sort of bring it full circle back to helping us understand what it means in terms of runoff losses from the end of the farm. So a really valuable contribution to the overall project and the investment program as a whole. So today, Arwen's going to give us a rundown on some of the technology that's been installed on these demonstration farms, and help us to understand, how she's tracking that water quality information back and feeding it back into the project so that we can evaluate the overall outcomes. So thanks, Arwen.
Thanks, Rob. Before we go into the presentation though, I just wanted to draw your attention to the equipment that we've got here. I'll be going through the results of the monitoring that we have actually done on this block right here. This, as Terry explained, is one of the Burdekin Irrigation Project blocks. We're doing basically two different types of monitoring on these blocks. We've got what we call high input monitoring, where we monitor both the volumes as well as also the concentrations of nutrients and pesticides. And then we have the low input monitoring, which is where we're just looking at volumes. So on this particular block here, we were just looking at volumes. To measure the volumes, what we've been doing is putting these flumes into the furrows in the actual cane block. This is what you call a Sandemus flume. It's not quite oriented right. When it's installed properly, it's quite important that you get exactly the right level. We have these flaps on the side, basically, that then go from hill to direct, obviously, the water from that furrow through. The way these are designed is it means that once the water enters this flume, it'll flow through at a constant velocity, regardless of the height, except when it's a really low dribble. So to basically measure what the volume is going through, we use a height logger like this. The height logger is placed into what we call a stilling well, which is this pipe on the side. There's a little hole in here. It's called a stilling well because obviously you want the water to be still when you measure the height. You don't want to be measuring in this column here when the water's racing through, because there's ripples and unevenness. So you need that to determine what the water level is when it's still. So you put it in the stilling well, and this measures the height. It's what you call a capacitance resistance logger. So it basically has a probe at the bottom, an electrode at the top and the bottom, and it applies a voltage through the wire, and obviously the water's conductive. So it can, with the differential in the voltage, it'll tell us what the height is at any given time. So that's placed in there, and that logs every 10 minutes. So this is placed at the bottom of the paddock. And basically the idea is obviously to get an idea of the surface runoff that's running through that furrow at any one time. At the top end here, where you've got the cups, we will measure how much water is getting applied per second in the irrigation. And then obviously once the water reaches the bottom of the paddock, the bottom of the furrow, it goes through this flume, measures the height, and then there's a formula that we use to measure what the actual volume of surface runoff was at the bottom. So you can place these flumes in the furrows. You can also place them at the end of paddock drain as well. But generally on these blocks with the high inflows and the long drills, there's just so much water that comes out at the bottom end that putting them in the end of paddock drain causes too much backing up of the water. So you're better off to put it in the furrows. The other interesting thing is, there is quite a bit of variability. Even though you might have the same inflow rates at the top end, there's often quite a bit of variability in the runoff at the bottom end. When the water arrives, how long it takes to get there, and also the amount of water. So that can obviously be the differences in the gradient in the paddock, the soil type in the paddock. There's all sorts of stuff that can go on that can affect that. So for this project, we generally put 2 flumes in the one irrigation set, and that gives us a bit of an idea then of the inherent variability within the block. I mean, obviously in the perfect world, you'd have these, in every single furrow if you could, but it's a time-consuming exercise to put them in, and it gets expensive when you've got to have loggers and do all the number crunching. And you know, it is the measurement that really takes a lot of time, as Mackenzie can attest, because she's the one that has to do the number crunching of all the data that we get. So for the BIP project, we're mostly interested in irrigation runoff. We're not so interested in the rainfall runoff. This one we're really interested in the irrigation runoff. And so we try to capture at least 6 irrigations to give us an idea. That covers the variability in maybe the run times and the inflow rates and the soil moistures at the time of irrigation. You know, 6 irrigations gives us a pretty good idea then of what's going on in that field. So we'll run it generally for the 6 irrigations. We'll try to get the inflows for every single irrigation and then compare that with what's coming at the bottom end, so that we can then give the grower some feedback on what proportion of water he's lost to runoff. So we know he's put on X amount, we know X amount has come off at the bottom end. The other neat thing that these guys do is they'll give us a hydrograph of the water height through the flume. So you can see, and I'll show it to you in a little while, a nice graph shows you when the water's first reached the flume and then how high it gets through the flume at peak flow and then as it tails off. So it gives the grower a good idea of what that looks like, the runoff duration, the runoff curve as well, and how that relates to when he switched off the water. So yeah, that's the infrastructure that we've used here. If you refer to the handout, you'll see a photograph of this installed at the bottom end of this paddock. One of these flumes with no water running through it. What's really important with these flumes when you're putting them in is to get the levels right, because obviously that affects the height through the flume and also the velocity of the water running through them. We generally put them up the drill a little bit because it's quite important that the water doesn't pool and then back up into the flume and give us a false height reading. So we generally put them up the drill a bit to try to avoid that backup water issue. So that's just looking at the flume at the outflow end, and you'll note there we've actually got 2 Odyssey loggers installed, so we always put an extra one in for redundancy in case there's some sort of problem. As anyone who's done anything in the field with equipment knows, you know, if there is going to be a problem, it's going to happen. So it's always good to have a spare. On the other side is just the inflow end of the flume, and you can see there where you've got the black rubber basically banking off that furrow from hill to hill. What you can do with these ones as well is we can actually run a couple of furrows into each flume if we want to. It's really important that we try to achieve a decent water height through these. You don't want to actually overtop them for obvious reasons, but you also don't want to just have a trickle going through them because they don't measure accurately when it's just a trickle. So one of the balancing acts is trying to get the amount of water coming in right. So sometimes we might put 2 or 3 furrows into each flume to get that sort of optimum height. And this particular farm, we had 2 going into each one. So I guess if you go across to the first graph, this was the very first runoff event that we captured after harvest. And this was basically when the grower was doing what we would call standard practice. So none of the automation equipment had been put in at that time. Agritech Solutions was just measuring the baseline irrigation practice. What you'll see with the graph here is the hydrograph that I was talking about. So we've got 2 flumes, 2 different colours of the 2 different flumes. We've got a time series down the bottom so you can see when the water arrived at the flume. We've got a dotted red line which indicates when the water was shut off, and this is really quite important for the grower to know as well. So with this standard practice, this was on a 24-hour schedule, so basically the irrigator would turn the water on. In this case it was turned on at 6 AM, turned off at 6 PM, and every irrigation was pretty much the same. Correct me if I'm wrong anywhere here, Ryan. On this one you'll see that there's a bit of a strange spike on one of the flumes, and that's basically where it normally happens straight after harvesting. There's quite a lot of cane trash. Gets collected in the furrows, unfortunately. Sometimes it can lodge inside of the flume, and then obviously the water backs up behind it and you get an artificial sort of rise in height, and that's what's happened here, we suspect. It's very hard to observe in the field because generally when you come after the irrigation it will have flushed out. I have seen it in the field. Occasionally I've actually come and seen one of these absolutely jam-packed, full of trash. Unfortunately, it's just one of those unavoidable things. These particular flumes are designed to minimise those kind of occurrences. There are other flumes that have a lot more angles in them and they generally will capture more trash. These ones are pretty good, but it still happens. So yeah, unfortunately that has skewed that result slightly. But the take-home message here is that you'll see with the dotted line, basically the water was turned off 9 hours after reaching Flume 1 and 5 hours after reaching Flume 2. So there was a big difference, obviously, in time between when the water reached Flume 1 and Flume 2, so that's interesting in itself. But obviously, yeah, the water had been running for quite a long time before it was turned off. After it was shut off, it continued to run through this flume at the bottom of the field for 8 to 9 hours. So that was after it was shut off at the top end. As Ryan mentioned before, you've still got that body of water running down the furrow and it continues to keep running for quite some time till that momentum gets through the field. So the duration of the irrigation was 24 hours, but the runoff itself ran for approximately 18 hours. That's the two flumes combined. So obviously one flume was a bit less than the other because the water arrived later. But that's quite a long time for that runoff to be occurring. And the maximum water height through the flume was 45 millimetres. And that's just interesting to note that when you compare that to some of the subsequent irrigations. So 45 millimetres through the flume is quite high. You know, there was a lot of water at peak flow getting through that flume. When we did the number crunching and we worked out how much water was applied in the irrigation and then how much was captured through the flume at the end, we worked out that approximately 25% of the applied irrigation was lost to runoff at the bottom end. So just keep that figure in your mind as well. When we turn over the next hydrograph, well, for starters, it's a more normal looking hydrograph. You don't have any weird sort of spikes and the two flumes follow a reasonably similar pattern. What we're wanting to look at here, just make sure you're on example 1. This is when this field had become semi-automated. So when I say semi-automated, it had the shut-off valves, the automatic shut-off valves, so the irrigator could turn off the valves and change the sets at any time he determined using the app on his phone. And so that meant that they could reduce those irrigation durations instead of 24 hours, which was a handy time, you know, 6 a.m. to 6 a.m. They could now turn it off earlier, so they could start it at 6 a.m. And turn it off at, you know, 3:30 a.m. or whatever, because someone didn't have to get out of bed and be paid overtime to go and change the set over. They could just do it automatically. The reason why I call it semi-automated and not fully automated is there's not end-of-row sensors providing information back as to when the water got to the end. So it's still required on either guesswork from the irrigator as to when they thought the water would get through, or if it was a decent time of day or night, them going to the bottom end and seeing when the rows had got through. But in this example here, the irrigation duration was 15 hours, so they've already brought it back from 24 to 15 because they now have the flexibility to swap those sets with the flick of a switch, basically, at any time of day or night. And what's important to note here is the water was turned off 3 hours after reaching Flume 1 and 2 hours after reaching Flume 2. So that's tightened things right up. They've really started to be able to turn off that water a lot sooner. However, the water continued to run through the flumes for about 7 or 8 hours after shut-off, so you've still got that time that it takes to get through the field. Total runoff duration was approximately 10 hours. So the previous one was 18 hours, now it's been brought down to 10 hours. And the maximum water height through the flume was 24 millimetres for one of the flumes and 31 for the other. So that's come right down from that 45 millimetres. So you can imagine what that does to the volume. So the things that will obviously impact on the volume is the runoff time and the height of the water through the flume. So basically what that's ended up as 11.5% of the applied irrigation was lost to runoff. So that's come down from the 25% for the standard practice. And that's really occurred, obviously, you've got the shorter run time, you've got the quicker shut-off time, and that's all basically then also related to a lower height through the flume, because the inflow rates were still the same. For both of those irrigations, inflow rates were the same. So really all that was changed was the run time and how quickly that shut that water off. And then the final hydrograph. So this is example 2. So this is another one that was done when it was semi-automated. And the only real difference with this one is that they've shut off the water even sooner again. So you'll see with the hydrograph, similar situation where you've got the 2 flumes and the water has come through the 2 flumes or arrived at the 2 flumes at a different time. This time it was 1 hour. The water was turned off 1 hour after reaching the first flume, but it was turned off before the water reached the second flume. But the water still got through to the bottom end at both of the flumes at quite a similar time, so that's really tightened things up. The runoff time was still about 7 to 8 hours after the shut-off, so same amount of water still going down that drill, takes that time to get down to the end. The total runoff duration was 9 hours, so that's come right down, even though the irrigation duration in this situation was 18 hours. So the last one, it was shorter. This time we've had a longer irrigation duration, but the actual runoff time has come back even shorter again. And the maximum water height through the flume has come down as well, 24 millimetres and 26 millimetres respectively. And when you do the number crunching on that, the amount of applied irrigation loss to runoff has now come down to 8.5%. So that's just, again, by turning that water off before the second flume had even started running through. So because that water generally keeps running through after shut-off for about 7 to 8 hours, that gives you a pretty good idea that, yeah, you can shut that water off before it gets to the end, knowing that it's still going to get through all those drills. So I guess if you were to go to what we call, sort of a fully automated system, you might put end of row sensors in, which means that you don't have to go down to the bottom end to check when the water's through. But you could actually move those end of row sensors up the drill and start to work out how long it takes for the water to advance down that drill and what optimum position it is or time you can turn that water off and still have all of those drills getting through at the bottom end. And that would then reduce your runoff time again. So on the final page here, you'll see just a table summary there of those 3 examples that I've given you. Irrigation durations coming from 24 hours to 15 to 18. So obviously irrigation duration is really going to depend on your soil moisture at that point in time and where your crop is, its soil moisture requirements, all those kind of things. So that's really where IrrigWeb comes in, and that will help inform you. You can't necessarily say, all right, well, a 15-hour irrigation duration worked this time, we'll just set them all on that. It's not always going to work that way, and that's why you've got the difference. But you'll see with the runoff duration that, we could keep bringing that back by reducing the run time and also shutting it off earlier and earlier. And that obviously affects the proportion lost to runoff. So standard practice was 25% lost to runoff, and that's a pretty normal figure. When someone asks us for a rule of thumb for what kind of, what proportion of irrigation is lost to runoff in the Burdekin, I always roll out 25%. So this one's spot on your average for your standard practice. And we've brought that down in example 1 to 11.5% and then down to 8.5%, again, by tightening everything up. And I imagine that if they get the end of row sensors in and start really looking at how that water's advancing down those drills, you could tighten that even further. So that's pretty impressive. So I guess, as I said, that was based on semi-automated. We've pulled this equipment out now because the cane's getting quite tall, it's starting to lodge. It becomes a real headache to get in there and get it out. And obviously, they will eventually be drying down ready for harvest. So with the BIP project, we're really interested in doing this kind of thing in other sites where we can compare standard practice, pre-automation, with semi-automation, with full automation, which we have done with other projects elsewhere in the Burdekin and got some really interesting results. And obviously we'll be interested also in monitoring the pesticide and nutrient concentrations and just seeing how tightening up the irrigation has an impact on that. Certainly some of the other work that we did with the Bry Irrigators project indicated that if you could tighten your irrigation up, obviously to have no runoff at the end, then obviously you're not losing any nutrient or pesticide to the downstream environment at all. But it also showed that, you know, if you can lower that water height coming down the furrow, that has the potential to reduce your nutrient and pesticide losses as well, because the water's not getting so high on the hill, it's not lingering there as long, it's not mobilising those nutrients that are in the hill and the pesticides as well that are applied, those that are applied to the hill as well. So that's something we're really interested in exploring further with some of the other high input BIP sites that we'll be implementing. Yeah, and I guess the only other thing really to note with this one was that we had these two flumes that you've seen on those hydrographs. They were only placed 3 rows apart, and yet you saw the difference in how long it took the water to reach the flumes, the height of the water through those flumes. Just gives you an indication of how much variability there can be from furrow to furrow, and that's why it's so important to do all these measurements and not just treat one block as a uniform block. You know, they do behave so differently at any one time. So yeah, that's pretty much all I had to say, unless Ryan or Terry or Mackenzie wanted to add anything else I might have forgotten.
Oh, I just want to say it's absolutely brilliant. I think it just backs up everything that Ryan and I were just saying. And just the fact, I'd love to see these in like dollars per hectare, these numbers. Like you start really focusing in on that. I think there's a lot of money to be made. And it's, again, the work that you do in the irrigation project is key to everything that we're doing. We're measuring on the volumes in, and we need to know when it hits the end, how much is running off. It's super important. So I think it's great.
Yeah, it's nice to not be doing guesswork, you know, to actually be measuring it and understanding the system better.
Just a question, not sure if it's for you, Arwen, or maybe for one of the irrigation specialists, but is there a trade-off? You know, like if we chase these numbers down even lower, is there a risk that you'll reduce your lateral soakage and have some other problem?
Complex beast. You know, you got to look at application efficiency, distribution uniformity, and also meeting your crop requirements. So there's a sort of 20-minute answer to that question. And
But is the short answer that you shouldn't be aiming for zero runoff or a tiny number, because there is it's necessary to have the water coming through and
depend on the paddock and the system and the moisture at the time of irrigation and a lot of factors.
Right.
So, but with furrow irrigation, a lot of the time a function of that is that you will get some runoff.
Yeah.
But like Ryan was saying before, the purpose of that runoff is not to fill up the recycle pit.
absolutely.
I think, again, what it highlights measurement, what Arwen's saying here, is that when we, and I was, like I said, I was a farmer and I was that person that said, it's a 12-hour set because that's what works for you. But we're actually starting to see it's a 9-hour set, it's a 10-hour set. And I think that's super important. And I think that next step, when you start putting those end of row sensors in, you'll get those gains again. I think you'll see those gains. So it's really good.
I could tell straight away as soon as the automation went in, because all of a sudden when I'd get in touch with the irrigator, when you're irrigating, when are you going to start, when are you going to stop? Stop time suddenly 11 p.m, 3 a.m. Yeah, and I knew straight away that, okay, now they're starting to use the system because that just wouldn't be practical previously.
Is to look at inflow rates. And automation gives you that opportunity because you don't physically have to be there. So the ability to tailor inflow rates could have a big impact on what's actually going on. And then that progression rate through the field. So had a little bit of experience with this sort of thing. And I think automation by itself is great, but the possibilities and the flexibility that it gives you to actually start doing things that you couldn't do before, I think is where the next progression is. So. Oh, I agree. I think that's the automation is the enabler.
Yeah, that's it.
So you actually have the process in place and you work out the measure. You measure. You come up with a recommendation, and then how do you do that recommendation? That's just an enabler that lets you do it.
And that's the other thing that was so good about this project is the process. It's no good thinking you know what you're doing. You actually got to know what you're doing, and the way to do that is to measure it. And so by having a standard practice or standard process, this is what we're doing, this is what we're measuring. Wow, okay, can we do better than this? Maybe we can. And then it's easy, like Ryan said before, you can put some numbers to it and say, you know, there's some benefit in this. and if we change what we're doing, there's some opportunity here. So
I think the only other thing I'd like to add is the demonstration sites, the actual demonstration sites, which I didn't focus on before. There's 3 full demonstration sites where Arwen will have her flumes in there. We'll have advanced sensors going down the rows. There'll be sensors at the front of the paddock measuring the flows on. So it'll be a fully automated replicated trial with 2 different flows, which is really difficult to do. And so we have 3 sites that's happening. One's getting worked on as we speak.
So those are those high input sites I was talking about. So instead of just having 2 flumes in, we'll have actually 8, and we'll have each treatment side by side. So it might be standard practice versus improved practice, or a high inflow versus a low inflow, side by side, several replicates. And yeah, it'll be very, very intensive because we'll be doing concentration and volume for all of those. And that information also will be fed up to the modelers, the Queensland Government modelers. So as we all know, a lot of the reef report card information is based on modelling outputs, and a lot of the growers are concerned that that's not necessarily based on real data from the Burdekin. These demonstration sites that Terry's talking about have agreed for the data from their sites to be used in those models. So that data will be used to validate those models and refine those models to make them more Burdekin appropriate. And it's also one of the first times probably that they will be given detailed irrigation data as well. That's something that those modelers have never had access to before. So it's really important that for the first time we'll be able to give them the level of data that they require to build upon and improve those models into the future.
And just the other thing I think was even highlighted here today was that the end of row sensor, while it's an ideal, it's something to work towards. You can see the gains that have been made without that end of row sensor. So I think it's important for people to understand that maybe 80% of the gain could be done at the top end, and then that end of row sensor closes the loop, but don't stop because we haven't got that 20% at the end. I think there's enough gain in the front end to be able to. We're working on this end of row stuff, and there's ways to do that, but don't not do it because of that. I think is a pretty key message.
No, that's a really, really good point. And as you say, the automation means that you can fiddle around with things and experiment, and it's not going to cost you a lot of time to do it. Yeah.
Right, can I put you on the spot? So this is money for your company, like in terms of this is saving energy and labour and pumping time and all sorts, or at least you're able to reallocate labour. What's your payback period? You got any idea yet?
We'll let him know.
Yeah.
I think some of the initial stuff that Sherry and Steve brought back to us, I think it was as short as 5 or 7 years for the investment that we made. So as long as the lifespan of this equipment is 10 years, yeah, we're making money. And obviously, price of energy is going one way, and that's up. So anything that we can save, and it's not just the pumping side of it, like Terry was mentioning as well, and even Arwen mentioned the nutrients that we applied, they're gone through the roof. So we want to make sure that every gram of nitrogen fertiliser that we put in that crop stays within that soil around those root zones and not pumped out at the end of the paddock. So yeah, there's a lot of costs in the background that we don't actually probably measure well enough, but yeah, it all adds up to pretty big numbers pretty quick.
This down at Spotswood years ago for us, like it was only a small paddock, and Gary just thought it was just a little trickle of water going down. It ended up being 7 megs every irrigation event he was losing. So, with just that information, he was able to then co-invest with us and do other things on the property to reuse that water, which was really good. So it's that real light bulb moment when they see it's not just a little creek like that that's flowing, it's actually quite a bit of water at times. So they're really good, really handy tools.
Yeah. That one was placed at the in the end of paddock drain. Yeah.
Ryan about payback. That's all going to be dependent on the block and the paddock and the shape. If we get a Delta farm, we could be a 6-7 year payoff time. We know that it's one right now that could be only a 3-year payback time. So it is going to depend, again, on the soil type, the paddock shape, all those things.
But the big benefit of this project is it's included, that all of the analysis is included because you're collecting the data, and then you've got DAF and others that are there to be able to add to it. Caleb, does the feed tool have the like the capacity to actually help people make decisions like this?
You can add multiple pumps to your farm. You can set them up with different flow rates. Every level of detail, tariffs, all the new tariffs that are really complicated.
Of automation as well? Could you include that?
You could, for that kind of comparison, you could include it as like maybe a fixed cost difference from year to year. But there are more complicated investment analyses that in a project like this, I'm not sure if we're doing that yet, but we'll soon see. We've just had some staffing changes recently, so, but I'm of the understanding we'll be more involved in this project.